to Physics 2, the fun part, okay? So we wrapped up circuits last class on Teams, it's been recorded, and it gave me the idea, like, and I think I had this idea a while ago and I just forgot to implement it. I'm gonna be recording this lecture right now. The audio may not be great because it's just coming from my iPad and I'm moving around, but it will be recorded so you can see what we covered. We're going to be talking about magnets, okay, one of my favorite topics. In magnetism, we're going to be looking at another type of attractive force, right? You guys all already probably know that magnets are attractive. You stick a magnet in a refrigerator, right? It sticks to the refrigerator. So we're going to talk about that. So here's all the videos you could watch from the publisher. So let's get acquainted with magnetism. So again, like as soon as we start a new topic, what we do first is we kind of pretend like we're in a lab, we're doing a bunch of experiments, and we're going to just qualitatively look at what happens when we do this and what happens when we do that, and then we'll construct our natural laws about the phenomenon that we're studying. So we'll begin our investigation by looking at some results of simple experiments, and I have a couple of these objects up here that I can do the experiment with, okay? So the first experiment is using a bar magnet, and you let it float in water, okay, so that there isn't any friction. And what you can do is you bring a compass nearby, and what you find is that the compass needle will align in the same direction as the north pole of the magnet. So from this, we can use a compass, which is essentially, like, what is a compass needle made of? It's made up of a magnetic material, a material that responds to a magnetic field. So as you'll come to find out soon enough, Earth creates magnetic fields, and so what the compass does is it senses Earth's magnetic field, and it pivots its little arrow to point towards the magnetic north pole. Okay? So I have a magnet right here. I could show you. Oops. A compass. Did I say magnet or compass? Compass. It's coming. Okay, so here's our compass needle. So as you can see, as I rotate this device, the compass stays, the needle stays pointing in the magnetic north direction, right? No matter how I turn that thing. And so if I bring the north pole of a magnet nearby, I can influence, whoa, see? He's already influenced, right? He's attracted to north pole. And the other side's attracted to the south pole. So you can see I can influence the compass, but if I take any magnetic fields, extra magnetic fields away and allow it to only sense Earth's magnetic field, it's going to eventually stop spinning and realign with Earth's magnetic field. See, it's making its way. It's oscillating. So that's experiment number one, okay? Devices, objects, magnetic objects can feel magnetic fields, okay? And there's a force on that object as a result. So, experiment two. We have two bar magnets, and these bar magnets are characterized by a north pole and a south pole. And so when we bring like poles together, either north or south together, we see a repulsive force. Okay, a lot like when we brought positive charges together or negative charges together. So I have two bar magnets here. I'm going to turn this one around. Okay, so that the same poles are facing each other. I'm going to bring them close, so they're already going to turn away. Right? As soon as I bring them close, they will go. And they spin around so that the opposite poles are attracted. Okay, so same side poles that repel and like attract. So you probably already had, some intuition about this. Experiment number 3, I won't be doing this one in person. I do not have a saw big enough. If I were to take this bar magnet here and cut it in half, what would happen? Would I have the north pole on one side and the south pole on the other? I would not. So each of these pieces would spontaneously produce the other pole. Okay? There is no magnet in existence that only has one pole. Every single magnet that we know about has both poles. And even if I could cut it a million billion times into the tiniest little piece, even down to a single electron actually has a north and a south pole as well. Okay, so everything we know has a north, everything that's magnetic has a north and a south pole. So this is a lot like, a lot of people miss this one on the exam. For charges, remember, a positive charge and a neutral can attract. A negative charge and a neutral can attract. The same rules for magnetic materials. North pole is magnetic, south pole is magnetic. They both attract non-magnetic objects like a paperclip. Okay, paperclips are not inherently magnetic. Like if I bring a paperclip to another piece of metal, they're not going to stick together because the two paperclips are not magnetic. Okay, but if I bring a non-magnetic item, a non-magnetic metal towards a north pole or a south pole, it will stick. Okay, so you don't need to be magnetized in order to feel the attractive force between the two objects. One object can be neutral, okay? So, on the other hand, you have non-magnetic metals, like copper, like a copper penny. It is not magnetic at all, okay? It will not ever be attracted to a magnet. Okay. So certain materials have this inherent magnetic behavior, other materials don't. Okay. There's a few on the periodic table that are magnetic: nickel, cobalt. Nickel, cobalt, iron are the 3 main magnetic materials. There's others too. Okay, copper, not magnetic. Plastic, not magnetic. Aluminum, not magnetic. So if we bring a magnet near an electroscope, so what is an electroscope? That is like a neutral sphere that we looked at when we were examining electric fields. If you bring a magnetic object near an electroscope, nothing happens, right? So if we brought I guess, maybe I didn't show you the electroscope. Now I'm thinking about it. Let me kind of tell you what an electroscope is, and then it'll make sense. So if I bring a charged particle, plus Q, nearby this thing, what will happen is these two little plates, they're actually little films that they'll separate, okay? Because they'll get charged positively and they'll be repulsed by each other. And so what this experiment is telling us is that a magnetic object will not induce any charge behavior at all. Okay, so there's no charge behavior, nothing, no polarization, of the charges at all. Okay, so the magnetism and the electric field, the electric force are completely different and independent. So there are some similarities, right? What do these experiments tell us? Well, there's differences and some similarities between magnetism and electric force, okay? What were some of the similarities? Opposites attract, like repel. Opposites attract, like, they will, if you come up here, you feel it's like you can feel the repulsive force, right? That's similar, okay? A non-magnetized object can be attracted to a magnet. That's similar, just like a neutral object can be attracted to a charged object. But some differences, there's some differences too. More similarities. The magnetic force is a long-range force, just like the electric force, right? In order for charged particles to feel a force from one another, they don't need to be touching, right? You can have a charged particle here at 0 centimeters, and you can have a charged particle here at 5 centimeters, and they'll feel a force of attraction or repulsive. But the same thing goes for magnetic objects. They don't need to touch each other to exert a force. You can have an electric dipole composed of a positive and negative charge, okay? But charges don't need to exist in dipoles, right? You can just have a random positive charge floating around over here. You can have a random negative charge floating around over here. The difference with magnetism is magnetic objects only exist in dipoles. You cannot have a single magnetic monopole. Okay, the basic unit of magnetism is a magnetic dipole. So there are no monopoles at all, right? There's no single ends and there's no single south poles. They must exist together. The magnetic field that is sensed by a compass points towards magnetic north, okay? So a pole that repels a known south pole and attracts a known north pole must be the south magnetic pole, okay? So in other words, if I have if you know, we're facing south over here, and this red needle, which is represented by the North Pole, is attracted to the South Pole, then you know that what you have right here is a South Pole. It's kind of like a redundant, like an obvious statement, you know, but when you read it, it's like, what are you saying? Aren't you saying what I think you're saying? They're attracted. North and South are attracted to each other. Okay. So, and then kind of like what I mentioned before, you have magnetic materials and you have non-magnetic materials. Non-magnetic materials, you'll get no force of attraction or repulsion, okay? Only magnetic materials, whether or not they're magnetized, will be attracted to the north or the south pole. It's a magnetic material, but it's not magnetized. And you'll see what I mean later on. This one's non-magnetic and obviously not magnetized. So here's one of our favorite problems, right? Similar problem to what showed up on the exam, but now we're looking at it from a magnetic force perspective. So let's say we have a bar magnet and we put the North Pole next to this steel ball and we observe an attraction, okay? And then if we read the question, if the bar magnet is flipped over so that the South Pole is now facing the steel ball, what do we get? What do we get? What do we get? Okay. Do we get a repulsion? Do we get an unaffected or not sure? So this steel ball is not magnetized, right? There's no north and south pole on it, okay? It's not magnetized, but it is made up of a magnetic material. So it will be attracted. It's like, this is like our neutral. Think of this as like our neutral object. Neutral is attracted to both positive charges and negative charges. So non-magnetic, non-magnetized, let me write this better. Magnetized, okay, is like our neutral. It will also be attracted to the South Pole, okay? So you do see the correlation there between electric and magnetic. So it will also be attracted to the magnet. You know, kind of what we talked about here. So if you cut a bar magnet in half, you will end up with two separate north-south poles. So in which way do they spontaneously arise? Okay, so like if I cut this in half, what does this piece turn into and what does this piece turn into? So this piece will turn into the south pole And this piece will turn into the North Pole, right? Because when I cut it in half, what I'm creating is another bar magnet. North on this side, south on that side. Okay, creating another bar magnet. So those are our observations. So all of this is going on because these magnetized objects are creating magnetic fields around them. Just like charged objects create electric fields around them. So we're going to talk about the field created by these magnets. Okay? They create a magnetic field. Every magnet sets up a magnetic field around it, just like every charge. Creates an electric field around it. Okay, so when you have an interaction between the two magnets, what you can think of is the field model, right? Where you replace one magnet with the magnetic field created. And so then this second magnet is interacting with the magnetic field created by the first. Okay, so we're kind of like going into the field model. So instead of thinking about two magnets interacting, we're thinking about a magnet plus the field created by the second magnet. Those are the interactions. So the second magnet is existing, and then the first magnet is creating the magnetic field. Okay, here's the magnetic field lines, which we'll talk about more later. We'll, get into the shapes of the magnetic field lines. And so basically, we're imagining that this magnet isn't even there and that this guy is interacting with the fields alone. Okay? That's called the field theory. So when we see a compass needle suddenly shift, it's shifting, it's moving, because it's aligning itself with an existing magnetic field, the one created by Earth. So if Earth's magnetic field are the blue lines, and they happen to be pointing north on this page, well then the compass needle is going to rotate to line up and also point north, just like the magnetic field lines. So magnetic fields cause forces. Forces can cause torques when something rotates. So we're not going to go deep into torques, but just when you see torque in this slide, I want you to just think like a force applied to cause a rotation, right? There's a force arising that is causing the needle to move. So magnetic fields are vectors. So we're going to be dealing with vectors. Vectors, as you know, have a magnitude and a direction, okay? And there's going to be different configurations that produce different magnetic fields. So we're going to be looking at a few different configurations. And in each case, we're going to be given the magnitude of that field, and then we're going to use a special rule to determine what the direction of that field is. You can think of the direction of a magnetic field as the direction that the north pole of the compass needle points. So if you want like a little magnetic field detector, you can use a compass and you can walk around, and whatever direction the magnetic field is in the area, the compass needle is going to point along an exact same direction. Okay, so you can think, you're going to see compasses a lot, little tiny compasses in these figures. They're there to tell you what direction the magnetic field is. So we can visualize the magnetic field by sprinkling some iron, which is a magnetic material, little pieces of iron called iron filings, and we can visualize the magnetic field lines created by a bar magnet. So you can kind of see it here, and I'll show it in real life. Okay, so these little filings, they're all acting like little compass needles. And when they're in the presence of a magnetic field, they're going to line up with the magnetic field lines. So you can kind of trace the lines. You can see they go like this here, and they kind of sprout out from the poles. Okay? And then you can stick a compass anywhere, and that compass is going to align with those magnetic field lines. And they're going to point towards the north, okay? And away from the south. So let's look at a real life picture of this. Oh, I see. There's little magnets under here. Okay. Are there? All right, let's start our own. Let's make our own. Let's make our own picture. Okay, so here's the little iron filings, and they're in some liquid so that they're easy to move around. And let's get a little bar magnet and place it under here. Place it underneath. Not working. I don't know how he got those little. But these, so basically you can see where you have the strongest magnetic field is going to be at the poles, because you can see that's where most of the iron filings have been attracted. Okay, and you can see how the compass needle, oh, actually look at this. I think my pen's magnetic. It kind of moved when I brought it close. So you can see how they align based on, maybe they need to be closer. There we go. Okay, depending on where you are, they're going to point. Let me get my little, there we go. Along the lines, the magnetic field lines, which go from north to south. Okay, so I move my compass around, and my needle is going to point in a different direction, right? When it's right above, it's going to be kind of parallel to the magnet. And when I'm to the right, it's going to start pointing right directly towards the pole. So we need to visualize the magnetic field lines. They come out of the North Pole and into the South Pole. So the field lines coming out of the North Pole are going to line up with the red compass needle, okay? See, it's pointing, it's not pointing towards the North Pole, it's pointing in the same direction that the North Pole is pointing. Do you see that? The North Pole is the red here, the South Pole is here, going this way. The compass needle is almost that way. If I move it down a little bit, it'll be more parallel like that. Okay, so the compass needle tells us the direction of magnetic field lines. So the magnetic field lines point away from the North Pole and toward the South Pole. Okay, so we zoom in. The red needle is going to point away from the North Pole toward the South Pole. Do we see that? Toward the south. On its way toward the south. This is eventually going to curl around like that. So those are magnetic field lines. What about the vector, right? We were kind of like, we go between vectors and lines a lot, even with electric fields. What's the difference? Lines are just a representation. Lines can be rounded and squiggly. Vectors are always perpendicular, not perpendicular, tangent to the magnetic field lines. So red is the magnetic field lines, B is the magnetic field vector. So if we wanted to know the magnetic field at that exact location, it would be the vector that is tangent to the arc, the curved arc, which is the magnetic field lines. And then red is magnetic field line. Magnetic field vector is always tangent to the magnetic field lines. So, right, our little vectors exist everywhere in space. So essentially what the little compass is doing is it's telling us the vector direction at that location, okay? So here's the compass and the blue, the little compass is everywhere, and the blue vector is our magnetic field vector at those locations. Pointing towards south and away from north. So we have our south and north pole here, and we're directly to the right of the north pole. So which compass needle would correctly, this is the red, okay, would correctly indicate the direction. So it points away from north and towards south. And we are directly to the right of this. So what we kind of saw in our, right, we kind of saw this kind of thing going on, right? So our compass needle, probably B, right? Points directly away from north and eventually towards south when these loop all the way around. So here's a nice clean picture of the magnetic field lines and the magnetic field vectors of a bar magnet. Okay, so these arrows are going to be the lines because vectors are always straight lines, they're never curved. So if we wanted to know the magnetic field vector at any point, we would find the little tangent to that. So that would be our B field vector. Okay, pointing towards north, pointing towards south, away from north. So that's rule number one. And this, as you can see, is similar to electric fields point towards negative and away from positive, right? So a lot of people think of the North Pole as kind of being the positive and the South Pole as being the negative. Just an analogy. Okay, let's talk about Earth, because this can get a little bit confusing. So we have a North Pole and a South Pole, okay? The ones on the map, those are the geographic poles, okay? Those are not the magnetic poles. So a compass points towards the magnetic North Pole, not the geographic North Pole. So the geographic North Pole is near where the South Pole of the Earth lives, okay? So it can get a little bit confusing there. The South Pole is actually located near the geographic North Pole. So this is why the North Pole of a compass points geographically north. Even though we know that the compass points towards south, magnetic south, right? As we saw with our physical, magnet that has a north and a south. It points towards geographic north, which is magnetic south. All right? So the magnetic field of Earth, in this picture, it kind of looks like it runs parallel to the Earth's surface, but obviously up here, the direction of the magnetic field of Earth tilts down, right? It's not parallel to the surface, it's dipping down. So we call this the dip angle. So near the equator, the magnetic field created by Earth has a near parallel direction to the Earth's surface, but it dips down a little bit, okay? The farther north you go, geographical, the angle is gonna be a little more direct into the Earth and not so much parallel to the Earth's surface. So there might be some questions that refer to Earth's magnetic field having two directions. One direction being the horizontal direction. That is the parallel to Earth's surface direction. Okay, so when you see a Earth's magnetic field is horizontal, I don't want you to think like XY or, X, positive X, negative X direction, or I want you to think parallel to the ground. Parallel to surface. And then the other direction, the other component, would be the component that is pointing into and out of the surface. Okay, that's going to be the vertical. So perpendicular to the surface. So essentially what we're doing is we're taking this magnetic field vector here and we're splitting it into a parallel to surface component. That's going to be the horizontal. And a into the page, or into the surface, component, the vertical component, right? Just like we do X and Y, right? Vectors in an XY plane have a component in the X, a component in the Y. Well, magnetic field vectors, we're going to split them into components, but parallel to the surface and perpendicular to the surface. So, he didn't give me any currents. Yeah, because of the weight of this book. Organizes things. So guess what? None of you do this, right? Nickel, cobalt, iron, and these other metals, they're not the only objects that produce magnetic fields. You and me can actually create magnetic fields through electricity. Through current, right? So the way that we create magnetic fields to power our motors, right? Because we use magnetic fields all the time. We use magnetic fields to drive motors. We use magnetic fields to convert mechanical energy into electrical energy. And the way that we do that is we create magnetic fields by producing a current. So electric currents also create magnetic fields. A compass will react to the presence of a bar magnet, but it will also react to the presence of a current. I can actually, when your phone is not plugged in anymore, you didn't get a current to go through this, but this plug is not connected to anything. I wish I had, because this is a very good, I'll show it next class, okay? So you'll have to just take my word for it for now. Right? If I hook up a power supply to a resistor and a wire and I get current to flow in that wire and I bring a magnet nearby, you're going to see an interaction between the two. So electric currents also produce magnetic fields. The shape of the field line depends on the shape of the current carrying wire. So we're going to look at a couple different configurations. Okay? The first configuration we're going to look at is the very simple one. You just have a long, straight wire with current flowing through it. Okay? So I have a wire. I have it hooked up to the wall, right? One is the positive terminal, one is the negative terminal, and there's current flowing through. The question is, what is the magnitude and direction of the magnetic field created by that current? Okay? So we're going to picture our current kind of two-dimensionally, okay? We're going to have the current come out of the page now. So this picture down here, this is the current coming out of the page or going into the page. All right, that's the wire. You're seeing a cross-section of the wire. And the magnetic field that it creates is circles around that wire, okay? That's the direction of the magnetic field created by a straight wire. And you can see that the lines are clustered close together here, and they get increasingly far apart as you go away. That's going to indicate the weakness, right? A weak magnetic field, far away from the source, a strong magnetic field close to the source. Circular loops of current. So let's take that wire and let's bend it into a circle. Okay, I can't do that with my pen. But take that wire, bend it into a circle, pass some current. So what's the current direction? Right? It's going through here. This is a curve, right? It's going into the page right here, right? So the magnetic field lines created by a curved wire are kind of straight in the middle. Okay? They're straight in the middle, and then they curve where the wire is perpendicular to the page, kind of like in the first picture, right? So the magnetic field lines are pretty horizontal here in the middle of that loop, but the magnetic field lines near the actual current itself are going to go back to its original form of being little loops around the current. Okay? So we're kind of qualitatively looking at this, and then we'll get into the magnitude and the direction of the B field and how that relates to the current's direction. Because as you know, the current in this picture could flow this way, right? Or this way. The same way that the current in this picture could either flow into the page, or out of the page or into the page, right? So we haven't talked about that, but we will. We're just kind of looking at our experiments, right? We're looking at our experiments here. So then, let's say we have multiple loops of current. So this is actually what we use to make magnetic fields in MRI machines and cyclotrons and your car. I don't know, maybe you've heard of the word solenoid in reference to your car. If you've ever had a lot of car trouble, maybe you've heard someone throw around, oh, maybe the solenoid's bad, right? This is the way that we make magnetic fields, and I'm going to tell you why. Because when you wrap a bunch of loops together, what do you get? You get a really nice, straight magnetic field. Right? That's why we had capacitors in the previous chapter, right? We had capacitors with positive plates and negative plates. And why did we like capacitors? Because they created really nice uniform electric fields. So this is kind of like our capacitor in magnetic field world, right? We use solenoids because they create nice uniform parallel magnetic fields in the center of the solenoid, which it can be very useful to us to have a constant uniform magnetic field, right? Because then we know the value and we know the direction, and we know how it's affecting the particles nearby, like, for example, the particles in your body, right, if you're doing an MRI. So this is a solenoid, and of course this direction right now in the center is pointing to the right, but as you'll see, if we flip the current direction, right, if we just change the current from going into the left to coming out from the left, we can switch that direction, but we'll talk more about that. So we're going to use the right-hand rule. So all of these pictures, all of these directions were determined. You can determine them yourself by using the right-hand rule. So we'll go back and see what the current directions are now that we know this rule. So what is the rule? You take your right hand and you make your thumb the current. Okay, your thumb is the current direction, and the way that your fingers naturally curl is going to be the direction of the magnetic field, right? We saw the magnetic field had some curviness to them. So for the case of a single straight wire, if the current is going up, well, then I'm going to stick my thumb in the up direction, and my fingers are going to circle around that. And that circle around is going to tell me that the magnetic field is forming a circle, the lines are forming a circle around the wire, okay? And so if the current points down, then your direction is going to be in the clockwise, right? Looking from above, right? The blue line is counterclockwise. The blue line that I'm going to draw for eye pointing down is going to be clockwise. Okay, so let's go back to those pictures now that we know this right-hand rule, and let's identify what the direction of the current was based on these B field directions. Okay, so let's go to the first one. So we're going to take our fingers and curl them in the B field direction, so we can see they're curling counterclockwise. And the way that my thumb is pointing, in order to do that, my thumb is pointing out of the page. So in this picture, the current must be out of the page. What about this guy? This guy's a little bit trickier, but we can do it. I'm going to erase my lines. Right, we're looking at a slice of the loop, right? We have a loop, and we like stuck half of it into the board, and the half that's sticking out of the board, we can't really see. All you can see is the slice down the middle. So let's take our thumb, let's look at the top of the loop. So if my fingers are curling in the B field direction, which is counterclockwise, my thumb must be pointing out of the page at the top of the loop. Okay? So I'm going to represent that with a dot. Little dot. And at the bottom of the loop, so the current moves in a circle, right? So I'll take my thumb and I'm going to move it in an arc out of the page, and then move it in an arc into the page. And I'm going to put on my fingers. You can see my fingers are now curling clockwise, right? At the bottom of the loop. And look at the direction of my thumb. It's pointing into the page, which I'll mark with an X. So the current is out of the page here, in page here. Okay, because it's a loop, right? So the current is going to flow in the circle, coming out of the page at the top, into the page at the bottom. Does that make sense? We're going to be looking at a lot of different simple objects, but in 3 dimensions now. But obviously we can't look at stuff on screen in 3 dimensions, so we have to look at different viewpoints of that 3-dimensional object. And this is one of them. This is like a slice view. Okay? So now let's look at this guy. So let's pick one of these. It's kind of hard to do without, let's do this. Let's pretend that this is where the wire is, the current's coming out or going in. Does that make sense, right? I'm taking a wire and then I'm looping it around like this. It's going to come out the bottom. So if we have magnetic field lines, that's our finger direction, going like this on the top, then the current must be coming out of the page at the top. Okay? So all those little currents, those slices, are going to be currents out of the page. And all these at the bottom, they'll be going into the page. Little X's. So the current then would be flowing out through here and coming in through here. Okay, we'll do a lot more of these. This is just our initial practice as we, go through this slide. So there's our right-hand rule. Okay. This is kind of what we already did. We're using the little compass to determine the direction of the magnetic field lines. So current pointing up on the left means your B field is, well, looking from the top, is moving in the counterclockwise direction. And then current down, we're looking at it from the top. My fingers are going in the clockwise direction. Okay. So this is like what we're going to use to denote into the page and out of the page. X's for into the page. Think of the little arrows, like if the vectors are arrows and there's the little feathers, right? And then coming out of the page is the little pointy needle arrow coming right at you, okay? And so then the compass notation, like I had already mentioned, right? The compass notation, it points along the magnetic field lines, right? So the little red needle is going to point in the same direction as the arrow of the B field. All right, so let's use the compass notation here. So what direction is that current coming? Into the screen or out of the screen? So our fingers are going to go in the direction of the red. And then to do that, my thumb is going to naturally point out. All right, but first, before I do my thumb, I'll take my fingers and I'll point them in the red. And then I'll extend my thumb out where it belongs. And then that's going to be an out of the page, out of the screen, which is represented by a dot. Okay, here's a good one. So P, okay, I'll use my pen here. So point P is like out here, okay? It's not on the pen. It's just that you can't tell because you're looking at it from this, right? So my pen is the wire. Point P is right here directly in front of it. What is the direction of the magnetic field? Where I put my fingers on. Okay? So we're going to stick our thumb in the direction of the current. And then I need my fingers to swirl around, but when my fingers are curling, they're representing the lines of the field. I need a magnetic field vector. So what I'm going to imagine is while my fingers are creating a circle that goes like this, right? Out of the page at the top and the page at the bottom, I need my fingers to pause at P and create the tangent, right? So that's going to be down. Right, so if my thumb is in the current direction and I'm circling, right now I'm behind the wire. Now I'm in front of the wire. My fingers are pointing down. You see that? Because that's the vector direction, right? It's tangent to the circle made by the lines. So the field lines go like this. And then the vector, let me kind of draw it so it lines there. There we go, right? The field lines go like this. The vector is going to be the tangent to that, which is going to be a downward direction. Okay, does that make sense? So we're really testing our three-dimensional abilities to view 2D objects as 3D right now. You can use your imagination for that and flex your 3D muscles. Okay. So let's skip this one because this one's a lot like, because we got a lot to get through. All right, can't do everything. I think we are doing a lot of good practice though. Okay. The magnetic field of a current carrying loop. So let's analyze that a bit further. So the picture that we were looking at, this is how you can think of it, right? Here's your loop. You cut that loop in half. Half of it's sticking out of the paper. The other half is going behind it. This is how we're going to view the loop. So what direction should the magnetic field be in this picture of this green square on the right? So you're going to take your thumb, stick it in the current direction, coming out of the top. And then right now, where's my thumb? It's in front of the loop, right? It's in front of that picture. So when I curl my fingers in, I'm like in the middle of the loop, and my fingers are pointing towards me, towards your right. Okay? So the magnetic field here in the middle of the loop would be pointing to the right, because it's creating a bunch of circles. Wait, hold on. Hold on. Yes. Okay. Yes. Just making sure. So you're right. So here we go. Right. There's our little counterclockwise circle. Here is our clockwise circle. Right. On the innies, on the inside, you can see both of those arrows are pointing to the right. When you get below the current, the V field is pointing to the right. When you're above the inside current, your vector, V vector, is pointing to the right as well. So in the middle, you're going to have all the vectors pointing to the right. Let me make it a little bit cleaner. Okay? You have a bunch of these, right? Okay, so the current loops are a little bit difficult to visualize. Here's a schematic for you guys to look at. Look at it, later. Analyze it later when you're studying. Okay? So here's kind of what I just did. Let's practice it. So what is the direction of the magnetic field right there? Okay, in the middle of the loop. So you can start by drawing your little circles around the currents coming into and out of the page. You know that this must be counterclockwise. This one is going to be clockwise. And everywhere in the middle, they're going to line up like this to follow these. Okay, so to the right. Okay, this one always trips me up. Okay, so, this loop is in a great magnetic field, and magnetic fields point away from north poles and towards away from magnetic north poles and towards magnetic south poles, right? So one side of this loop is going to be considered the north, and one side is going to be considered the south based on the magnetic field direction. So let's draw our little loop. So on this side, we have coming out of the page. So inside the loop will be a downward arrow, okay? Here will be another downward arrow. So over here would be a downward arrow. And so magnetic field lines point towards magnetic south and point towards away from magnetic north. So which is the north pole? It would be the top side of the loop. So we agree with that? Oops. See, I know I always get this messed up. I always get this. Okay, hold on. Magnetic field lines, okay, the compass points towards geographic north. I have to do this every single time. Compass points towards geographic north, which is magnetic south. So they point towards the south pole. Where, I don't know. I don't know why this tangles me up all the time. Okay, so let's do this. What if I take this all the way around? Oh, wrong way. No, that was right. Okay. So I think it has, we're going to come back to this. Let's come back to this. Okay. I don't think this is wrong. This is not wrong. It's just, maybe it is. I don't know. Let's come back to this, okay? We're going to come back to it. Magnetic field of a solenoid. We're going to think about why that's flipped. It'll come to me. So solenoid, that's our third configuration, right? We had the straight line, we had the single loop, now we have the multi-loop. That's called solenoid. So the solenoid, its purpose is to create a uniform magnetic field. All right, in the center. We use it all the time. And the field along the center is going to be very strong, which you can tell by how tightly those magnetic field lines are clustered together, right? It's going to be weak up here, strong in the center, and along a nice straight axis. So those are the qualities of a solenoid. So here we go. This is what we were gonna practice with the other solenoid picture. So if the magnetic field, now we have our current, you can see like where it comes in and where it comes out. We have our magnetic field going through the center of the solenoid pointing up. So the question is, which current direction would produce that? So remember, our thumb is the current direction. So we're going to have to kind of play a game. We're going to, let's for example, start with the top wire. So we're going to take our thumb and we're going to kind of curl it in as our thumb traces out the helix. Okay? So if I start my thumb moving from the top, I now, so this is where my thumb is. I'm going to put my thumb, hold on, my pen got messed up. Okay. I'm going to put my thumb right here, which is behind the solenoid, right? You see the dashed line? I'm going to put my thumb right here behind the solenoid. So when my thumb is behind the solenoid, if I want to see the magnetic field direction, I'm not going to curl my fingers behind my thumb because I don't care about the magnetic field behind the solenoid. I care about the magnetic field inside it, right? So I'm going to curl my fingers so that they're in front of the current, which is the thumb. And I'm going to see an upward direction. So I must have guessed right to begin with, okay? So the current is going to come in through the top because I can verify that when I curl my fingers in front of the current, which is my thumb, I get an upward. But let's just double verify it by looking at the bottom. So my first guess was I going this way, okay? Which means that I must come out this way. So let's try my right hand rule at the bottom. So my I is going to come to the right, but I need to make sure my fingers are behind I, right? To represent the field inside of the solenoid. And again, they point up, which is the, which I got before, so that's good, right? So I guessed correctly. So, this is where the 3D comes in, right? Your finger is the current direction, but are you looking for the field on this side of the current or this side, right? So, in this case now, so if this seems to work out, is it clockwise or counterclockwise? As viewed from the top. So if I'm looking down, I have my current coming behind and going forward like this. So to me, that is counterclockwise, right? Looking down. So this is the hardest part, is visualizing that 3. If you're in, organic chemistry and stuff, you probably got really good at that. So counterclockwise, as viewed from the top, right? Because it's going this way. So if you're looking down, that is not how the clock goes. So we've been analyzing the direction aspect of the magnetic field. Now we can have some formulae to calculate the magnitude of the magnetic field, right? The direction is governed by the right-hand rule. The magnitude, I'm going to just give you the magnitudes for each configuration because they're derived from calculus, and we're not going to touch that here. So before we get to that, what are the units of magnetic field? They are the Tesla. So that is the SI unit for magnetic field. 1 Tesla is actually a very large magnetic field, and in biological systems and even Earth does not produce a very strong magnetic field. So you'll be working with, fractions of a Tesla. So if we pass 1 amp of current through a wire and we're 10 centimeters away, like this, my face is only going to feel about 2 microtesla. Okay, not very strong. So Earth's magnetic field is just a little bit bigger than that. A strong refrigerator magnet, still fractions of a Tesla. MRI solenoid, about 1 to 2 to 3 Tesla. Okay. And then the world's strongest magnet, the strongest magnet that we can create, only produces 45 Tesla. So Tesla is a large unit. Just like charge is a large unit, right? We were working with fractions of charges. So here we go. The magnetic field magnitude created by a straight wire, okay? The magnitude is a new parameter, a new variable, constant, a new constant called the permeability constant. Its value is right here. This is also equal to 4 pi times 10 to the minus 7. So when you do 4 pi is 1.26. I mean, it's actually 12.26, but you move the decimal over. And okay, so let's take a look at the magnitude of a magnetic field created by a straight wire. Its magnitude, of course, is going to depend on how far away you are from the source, right? So the farther you are away, the bigger the R, right? So this R is the distance that you want to know the magnetic field, right? The distance from the source of it. So R is the distance from the wire, right? The source of the magnetic field. So the larger the R, smaller the B, and vice versa. I is obviously the current. And then we have our 2 pi in there, which comes in from, you know, some calculus. Okay? So it's a very basic equation, and this is for straight wires only. Okay? So here we can, you know, see how B varies with R. It drops off with the 1 over R functionality. Okay? And then here's our directions as a reminder from what we were just looking at in the previous section. So this is a great problem to do. This is like a test question for sure. So the question is we're going to compare the magnetic field at points A and B, okay? Which, you know, are they half as strong, blah, 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 right? So let's find the magnetic field of A, mu naught I over 2 pi R1 or RA. So the current is I, and our R is 2 centimeters. So I'm going to leave that as RA. And then the magnetic field at location B, same current, distance is a little bit bigger. The distance is twice RA, so I'm going to put in a 2 RA right here. Does that make sense? I'm going to divide the two to determine their relationship. So I'm going to get a lot of stuff canceling. I'm going to multiply by the reciprocal, right? I'm going to get all this going away. And, well, you can see that, oh, this should be RA, my bad, right? The RAs are going to cancel. And what I see is that BA over BB equals 2. In other words, if you want to write this as a sentence, the magnetic field of A is equal, to twice that of B. Okay? So compared to A, B is half, right? So if I want to complete the sentence, I actually need to write B as a function of A. So B is actually half as strong as A. Okay? So it's half as strong, so we know we're either working with A or B. And, well, what is the direction of each one? Let's do a right-hand rule. So thumb the direction of the current, and then I'm going to sweep my fingers until I am to the left of the current, okay? Which is where A is. A is to the left. As you can see, my fingers are pointing out. So outward. Now I'm going to keep turning them until my fingers are to the right of I at the location B, and they're pointing inward at that location. So the directions are opposite. So B comes out of the page here and goes into the page here. So they're opposite directions, and B is half as strong as A. So, boop. Okay. So there may be some problems where you have two or more sources of magnetic fields. If you want to know the total magnetic field at any location, you can simply add all of the magnetic field vectors together at that point. Okay? So vector, it's called the superposition principle, right? Principle of superposition. You can simply add the vectors together. So for example, let's say we have a wire here coming out of the page, and we have a bar magnet sitting here, and we want to know what's the total magnetic field right here. Well, we would draw our two vectors and we would add them together. And in order to add vectors together, you need to break them down into components, right? X and Y. And so we would do, perform those computations, just as you would add two electric fields together, okay? Here, the geometry is a little more complicated. It won't be as complicated like this. It'll be, X's and Y's, okay? So in this example, which we don't have time to do today, we'll come back to it in the next lecture. So this one I'll say we'll come back to because I want to do it together. Because we'll review everything. Okay, same with this. So now let's look at the magnitude of a magnetic field due to a loop, a single loop of wire. The magnitude, similar, but there's no pi, right? So you can kind of think of it, if there's a circle involved, the pi goes away. If there's a straight line, the pi comes in. So, right, the other one was 2 pi r, and this one's simply 2r. So the magnitude, notice how r is capital now, okay? Because this magnitude, we're only finding it at one location, right? The location directly in the middle of the loop. So that's how this equation is different. It doesn't, you can't just pick, you can't pick your different r's, right? It's 1r, which is the radius of the loop. We are only finding the magnitude of the magnetic field right there, okay, at the center of the loop. So this equation only works for the center of the loop. What is the magnetic field? At the center of the loop of current carrying wire, okay? Now, the solenoid, right? The solenoid is multiple loops. So what we can do is if there's multiple loops, we can just multiply by the number of loops to get the total magnetic field at the center. And so that's exactly what we're going to do. It's going to be the same equation, except now there's n for number of turns. So we call a loop a turn, right? Because to make these solenoids, you take a straight wire and you turn it around a cylinder. So we call them turns instead of loops, but it means the same thing, okay? And so what we're finding here is a magnetic field, not anywhere, but only along the center axis of the loop, anywhere along the center axis, okay? Not anywhere around the loop, just on that center axis in the middle of the loop. So we'll come back to this. And we'll, work on our computations. So what's the difference between a solenoid and a whole bunch of loops? A solenoid becomes a solenoid when the length is much longer than the radius, okay? So that's when we call a bunch of loops a solenoid. So L must be bigger than the radius R for it to be a solenoid. And that just helps the uniformity of the field inside, right? Because look at the field lines here. They're all very, very, very parallel. Look at the field lines in this loop. They curve pretty quickly out, right? So it's not super uniform. That's why the equation is specifically for only the very, very center, okay? So when you have a whole bunch of turns, the more turns you have, the longer it gets, you're going to have a more uniform field inside. Okay? And so the equation for a solenoid, mu naught times the number of turns times the current divided by L. So you can see that 2 goes away. So finally, like, we got rid of the pi, we got rid of the 2, and now for a solenoid, we simply have the length. All right? So that is the equation for the magnitude of a magnetic field inside the solenoid. And we'll do this as our last kind of quick check. So if the magnetic field is going that way, where is the current entering? So our thumb is not the blue lines, right? Our thumb is the current direction. So let's pick one. Let's pick this and see if it's our answer. Let's pick this. So our thumb is going to go along the wire direction, and I'm going to curl my fingers when they're inside, like when they're behind that wire. And you can see my fingers are pointing in the opposite direction as B. So I know that I'm not entering in on the left. Okay. So I know I'm not entering in on the left. So let's try entering in on the right. So my thumb is the wire, and you can see in the picture I'm going behind, right? So I need to hold my fingers and make sure that I'm in front of that wire, and you can see that they are pointing to the right in this case. So entering in on the right is going to be correct. Okay. And so now as I bring my thumb, right, I'm looping around, coming like this. Now I'm on that first wire that is in front of the innie, and you can see I have to curl my fingers behind that to see a right pointing view. So I'm confirming it. So right, I stuck my thumb here, and then I stuck my thumb right here, and I made sure that my fingers went behind the thumb here. And then in front of the thumb here. Okay, so we got as pretty far that I wanted to get. We talked about the magnitude and direction of the magnetic field created by wire. And I'll show you next class what that looks like. Okay, let me know if you have any questions.
I just want to ask, 3, you're allowed to drop 1.
Yeah, so yeah, you don't have to go for one.
I don't have to. Okay.
No,
So just
I'll miss
because,
you.
because I have a conflict on.
Oh, okay, good, that works out.
So just go ahead.
Yeah. Yep.
I appreciate it. Thank you.
Of course. Oh, yeah. Oh, okay, okay. Yeah, I'll put, yeah, no, I'll push it. Okay, sounds good. Thank you. Oh, I'll do that first.
I had asked you, I sent you an email asking to see my.
Oh, I didn't get to it yet. I'll send it to you, I'll send it to you. Oh, okay, good.
And I was just looking at my Scantron and I looked at the answer.
Yes.
And
Oh, I know, I messed up.
I got a 12 out of 15 on the
Yes,
Kansas assignment.
yes.
I think I got more.
Yeah, I know, I messed up with this, basically.
But there was another one.
Yes, there was. So I did, well, okay, we got 5 right. So basically, everyone has 5 the answer was E, but it was not shown on good for me.
Yes.
Yeah. So that was, I might have accidentally, so you think I can. I'm deciding.
Because according to the answer, yeah, I got 14 out of 15.
Oh, you have more, okay, then I'll fix that. I thought I didn't want to take it away. Okay.
Yeah, yeah.
Email me and I'll fix it. Okay. Yes. Yeah. Yes. Yeah, so if you look at this wire, he's in front of the solenoid, right? The middle of the solenoid is behind it. You know, it's like this, right? So I'm gonna put my thumb, well, we already know the answer, so I'm gonna put my thumb this way, and then my fingers, I don't wanna look at them here, because that's outside the solenoid, I wanna look at them here. So you can see the fingers are pointing to the right. And so here, we can check it here, so if it's coming out of this, then it's going, entering in, so here, my thumb is going behind the solenoid, so I need my fingers to go in front of that to show the magnetic field lines pointing to the right.
And that means that the eye is like,
Yeah, so this one, I tried going in here and that was wrong, so it's going in on this side, going in on the right, eye is going like this. And then the field. Yeah, it'll take a couple, you'll get it, yeah, so here's a
Yeah,
better, this one's a better visual, I think. Okay, and then this one, okay. I know, we got this one, it was the North Pole, South Pole one, I don't understand, cause I ran into this, like, why? I don't know. So the magnetic field lines go toward the south pole, magnetic south pole. I think it has to do with being inside the magnet. I'm gonna.
this is
This is
another
the
one.
Oh, yeah, this one we got, this one was fine.
Yeah.
It's just calling it north and south is where the issue
Okay.
comes in. The B field direction, easy to find, it's just like, is it the north and the south? I'm like,
Yeah, this one I think that it's so
yes, so for this one, so, yeah, so if the current is coming out of the page at the top, so I just went like this.
look at that how
And then my fingers are gonna go tuck inside of it, so they'll be coming out of the top and into the bottom.
and what about this one?
Oh, that was like the exit, that's just like, it's hard to tell, like the way I drew that line, it's just exiting the.
Okay, but not, you're not talking about these ones.
No,
Okay, that.
yeah, oh, okay, yes, yeah. Okay, you're welcome.
I've just got a question. Why is like confused? Like why is like one metal
I know.
magnetic and then one
Yeah,
not?
so some metals are magnetic and some aren't. It has to do with their atomic structure and the electrons and which ones are on the valence and which ones are at certain orbitals. So if you look at I don't have a periodic table of elements, but the nickel, iron, cobalt are all right next to each other. Because they all have a
Okay.
similar.
So I also did like paired electrons or whatever.
Yes, exactly. Unpaired electrons cause magnetism.
Oh, okay. Okay.
That's exactly what it is.
All
Yeah.
right.
Mhm.
Thank you.
Hello.
I have a question.
Okay, yes, yes. Mhm.
This is the current, right?
No, the blue is the magnetic field line. So, and our thumb is gonna be the wire. So, we're on this side, you can see the wire's behind, right? So, our thumb is the wire, then we want our fingers to end up being in front of the wire. And so I need it to represent the magnetic field in front of it, right? And so then my fingers, in order to represent that, I have to curl them like all the way here, and they're in the Does that make sense, I guess?
And also you can have hours tomorrow?
Yes.
Yes.
Yeah, I think someone's coming, but that's fine.
Okay.
Just one person.
Thank you.
Okay, you're welcome. Okay.
That's the one right after.
Oh, you did, I didn't see it, because I had like 1,000 people. Oh, you wanna look at it, is that what you wanna do?
Yeah.
Okay.
Everton can.
No, we can, well, okay, let's actually do it on, what I can do is we can do it, because I realized I don't know where the solutions are.
Okay.
So that way we would take this extra time.
Okay.
Yeah, I was like, where are my solutions? I was on my computer, I didn't find them, so.
Okay.
I gotta solve it.
Cool. I didn't watch the Teams lecture,
Okay.
so I didn't come to this lecture either
Oh, okay.
because I felt like I'd be lost.
Oh, okay.
Can you post the Teams lecture?
Oh, wait, hold on, let me stop this record. Speaking of that, hold on.